programming language, which I'll be honest, full disclosure, I haven't actually used in anger for about 12 years. So if someone asks a question I don't know the answer, it's probably because I've forgotten. But the main purpose of this talk I'm going to talk about is it's actually originally this talk was going to be why dynamic systems don't give you the benefit you think they do. But actually, when I came down to it, I thought actually they still do, but maybe the dislike for static type systems is a bit misplaced, because a lot of people feel that when they're using static type systems, they have to write a lot of boilerplate code and a lot of excess code in order to get what they're doing, and they have to change a lot of code in order to make changes. Now, Haskell is a statically typed system, but it uses slightly different approaches to solve those same issues. And mainly those come down to having a very powerful and very flexible type system. Okay, so I'm only going to talk about one particular part of the type system. I'm not going to go into details of the entire type system because that would take hours. This is only 10. So this is an example of an algebraic data type, and this is where people like Mark can tell me what my understanding of cards is wrong later on. So this actually is there's three data types declared here. We have a suit type, which is pretty simple. This is what is called a discriminated union as well. So we have 4 different values of the suit type. These are actually called constructors, these things. With spades, diamonds, hearts, and clubs. And this little thing on the end, this deriving show and equal. These show and equal are actually called type classes. And what show and equal do, it says, this type called suit, I want to add some function to that will allow you to convert it to a string. That's what show does. And EQ says I want to be able to test for equality and inequality. And the default implementation knows how to do these particular types. And so you don't actually have to write any code for show and EQ at all. So there we've already got a type that you can convert to a string and you can test for equality of the values of that type. Okay, and then the second type we know is rank. Is pretty much the same deal. 2, 3, 4, 5, 6, 7, and so on. Jack, Queen, King, Ace. It's also got 2 other type classes on here. It's got ord and enum. So order, basically what that means is that you have an ordering along these particular types. So it knows that 5 is greater than 4 and 6 is less than 7. So the ord actually gives you the less than or equal to, gives you less than or equal to or greater than. And if you specify EQ as well, it's clever enough to automatically know how to do less than and greater than or equal to, because it can work out those from those other functions it has. Enum, anybody who's used to languages that have enum, it's absolutely nothing like that. What enum is a bit like specifying an order. It's almost like another ordering. So it says you've got 5, and it specifies what the predecessor and the successor is. So the predecessor of 5 is 4, the successor of 5 is 6. So you can actually step through them in order. And then now we have our first kind of complex algebraic type, which this time here you'll notice there's a duplication of the word card. This is because there's no discrimination here. You're not saying this is multiple different versions of the same type. This is the same version of the same type. So a type called card, but it takes 2 parameters, a rank and a suit, which are our previous things here. And that defines everything you need to do to any card in a plain deck, plain cards. So you've got your rank and your suit, and you've got your pay. So I should have got a drink of water before I start this. Okay, this is deriving the show, which I've already spoken to before. And this is some special code that allows you to change the default implementations of the equal and the order. So I'm not going to go into the details of exactly what this code means, because I'll get into pattern matching and that will take another few hours. So but basically this says we're going to ignore the suit for when we want to test for equality. We're just going to look at the rank, we're not going to look at the suit. So the king of diamonds and the king of spades will be equal by the equals definition. And there's a similar deal down here with the ord. This is saying that we only pay attention to the rank again. So we don't pay attention to the suit. And you'll notice on both of these that we haven't had to redefine all of the different operations that you can do in those classes, type classes. We've only had to define enough for it to work out the others. So I think my next slide is, so we can actually show how to use those types now. So we have, so this is just like you're typing into a REPL. I don't know if most people know what a REPL is. You just type commands, it's like we're typing the code, and it executes it immediately. So we're defining a variable called 3 spades, which is the value of the card for 3 of spades. That's it, that's how we define an instance of the card type in the 3 of spades. It's that easy. Another one of the 3 of diamonds, this card of 3 of diamonds, that easy. We can then test for equality, and it tells us it's true. And we can also put the types directly into if we want, and we can also test if one is greater than the other, because that's false. You'll notice here that we've never actually had to say what the types of these variables are. It just knows, because the type inference system in Haskell means you don't generally have to write all that rubbish. You can look it up yourself. If the code's really obvious, it does it. You can tell it if you really want to. Generally, it's not recommended though, because it just adds clutter to your code. If you're used to dynamic systems, that's probably fairly normal for you. So. Okay, so now there's a slightly more complicated one. So this combines the 2 things that we've had before. So it defines the hands of poker. Just tell me if I'm wrong here.
No, that was good.
That's good, that's good. Yeah, so we've got a high card hand, and this is a list of cards. So the square brackets mean that it's a list. Okay, we've got a pair of, which you can take a rank, so you can say a pair of 3s, and it can show you what the actual hand is. 2 pair shows you what you've got, a pair of 3s and a pair of 5s maybe. 3 of, and so on and so forth. I think I need to go through all of those, do I? But the great thing about this as well is you've also defined an ordering on here. So you've already said the full house is better than the flush. You've had to write no code to do that. You're just leveraging the type system to do all of that work for us. I'm not going to talk through this code. This is quite, but I just wanted to show a few little things in this piece of code. First thing you'll notice is there's only one type declaration in this entire piece of code. That's this thing at the top here. The double colon basically says make hand is a function that takes a list of cards and returns a hand. That's all it is. This is a function, make cards, list cards, and this is the code to do it. And I tested it and it actually worked. This was quite pleased. I'll be honest, I copied most of it off a website. Yeah, there's a few pieces in here that are not so obvious to read because of one annoying thing about Haskell is that it was designed by a lot of mathematicians and they like to use really short and meaningless words for names of things, like pred. That's really good. But to try and demonstrate a little bit that that's just an artifact of the people who write it, not the actual language itself, there's a great line of code here which is, if it's a flush and if it's a straight that's sorted, then it's a straight flush, otherwise it's a flush. It almost reads like English. It's not quite there, but I don't think many languages are quite exactly like English. Yeah, so I'm just going to show how this works. Make hand, with that in there, and it comes you back with this full house 3-5. Again, can you tell me if that's right? Yeah. And make hand of those particular cards. It's 4 3s. Again, we haven't had to write ridiculous reams of code in order to write something that's really quite simple to understand, quite simple to follow if you understand the make hands code. But there's no messing around with type signatures that you have to write out constantly and over again, and if someone changes it, you have to change it 1,000 places. There's none of that nonsense. It's just nice and simple. That's it. I think that's my last slide. Any questions that I can answer?